So we finished off talking about the elevator questions. I do want you to understand that lots of things can be an elevator. So like a bungee jumper is an elevator. Throwing a rock up in the air is an elevator. Anything moving vertically is an elevator because gravity is pulling down and something is pushing up. In any situation where there is a strictly vertical movement, it's an elevator. Just so you know, context matters. Because sometimes I throw a question just like that last one on a quiz or an assignment or something, and it's like someone throws a rock up in the air, and I only give the upward force, and everybody forgets that gravity is for some reason there. Okay, and they're just looking at, oh, well, he threw it up in the air with 100 newtons worth of force. That's the only force. Well, and they're off. Okay, well, you forgot about gravity. Just because you're throwing something up in the air doesn't mean there's no gravity anymore. So remember, anything that's moving vertically is technically an elevator, and gravity is always part of that kind of a question. Today, we're going to talk about systems. So these are Newton's second law problems where there is more than one mass. Now, with more than one mass, we have to consider that problems can be dealt with as a whole, as a system, or we can look at individual parts of the system and then apply things to the whole. Right? So what I'd like you to do right now is copy this question down, because we're going to walk through it as our first system example. All right, I'll give you a few minutes to get it copied down, including the diagram, and then we'll talk about it. So in this question, we've got two blocks. They're made of the same material, which is important because that affects how much friction there can be and things like that. They're connected by a light rope, so that's this rope here, on a level surface. An applied force of 55 newtons to the right causes the blocks to accelerate. While in motion, the force of friction on the system is 44.1 newtons. Calculate the acceleration of the blocks. All right, it's right now showing two separate blocks, but all the information I'm given is really telling me about the whole system anyway. Can I make that one mass? I absolutely can, because those two blocks have to accelerate together. They're connected. It would be impossible for one of them to accelerate faster or slower than the other. If that happened, one of them would catch the other, or the rope would have to break. And that's not happening. Once the rope breaks, they're not a system anymore. So they have to have the same acceleration. And that's the thing we have to kind of remember about system questions. The parts of the system have the same acceleration, at least in magnitude. If you have a pulley, like we looked at yesterday, you could have a difference in direction, but the magnitude of the acceleration is the same for any two masses that are connected, two or more masses, in fact, that are connected. So I know then that I can simplify this diagram down to this. I can say that there's 30 kilograms worth of mass. It's being pulled this way by 55 newtons worth of force and resisted by 44.1 newtons worth of force. Okay? It doesn't matter that the 55 newtons is actually only pulling on the front mass. They're connected, so it's actually pulling on both of them. Okay? At least from this perspective. The next question we do will actually isolate the two. All right, so right now, can I calculate the net force? I can, right? I've got 55, I've got 44.1, so that's going to be 10.9, right? F net will be the vector sum of all forces, so we'll say 55 plus negative 44.1, or just minus 44.1. And we're going to get 10.9 newtons, and that'll be forward. Or it says to the right in the question, doesn't it? Right, yeah, it says right in the question, so my answer needs to also reflect that. How much mass is that 10.9 newtons accelerating?
30 kilograms.
30 kilograms. So now, if I want to calculate acceleration, F net over m, 10.9 newtons divided by 30 kilograms, because it's accelerating all of it. 0.36 meters per second squared. Right. That's my acceleration. Having a system doesn't really change what you do. We still did sum of all forces. We still did F equals m times a. We did have to be mindful that both masses are going together, but that's really about it for being different. Now, the next step to a system question is they'll ask you about forces in the system. Right? So they only told us that there was this force here from the hand and that friction on the two blocks added up to 44.1. The next thing they could do is say, the friction on this block was this much. Calculate this other force that was within the system. Right? That's the next thing we're going to look at because that's the next question here. So we're going to do number 2 first because that's the one I was just telling you about. So we still have the same two blocks. The acceleration that we just calculated is still the same. We can still use that number. So now, what they want you to do, is, or what they're telling you is different rather, is that the force of friction on the 10 kilogram block, so the front block, is 14.7 newtons. Calculate the tension in this rope, the one that's connecting the two blocks. Okay? That's the next thing that they want you to do. Okay, don't do B, because I have no idea why they would even ask B. Why would they even ask B? Why do I look at that and go, why would you even ask that? Why would you ask me for something you already gave me? This is, I mean, the hand is what's causing the whole thing to go. That's 55 newtons right there. They already told me what it was. I don't know why they'd ask you for that again. So let's focus on A for right now. You can solve this question, or let me rephrase that. You have to solve this question by isolating the blocks. You can solve it with either one. You can solve it with the 10 kilogram block or the 20 kilogram block because that rope pulls on both. So in this question, they give me one of the forces that's internal or inside of the system. It only actually directly acts on one of the parts of the system. So here's what I have to realize. Each one of those blocks has the same acceleration. And since I know that acceleration, I can calculate the net force on just that part of the system because the acceleration applies to all of them. So I can isolate a single part and then find out the information they want about that part. The easiest part to do it with is A. It requires one less calculation. You can solve it with the 20 kilogram block, but you have to do one more calculation. It's subtraction, so it's not that hard, but it is one more calculation. So this is what I'm going to do. I'm going to say, all right, you told me in this question that the 10 kilogram block has a force of friction acting on it of 14.7 newtons. That's, yeah, 14.7. The 10 kilogram block is being pulled this direction by the hand, 55 newtons. What other force is acting on that first block? The other block. Is that what's causing there to be tension in the rope? It is. If there was no block tied to the back of that thing, just the rope would just drag along the ground. There wouldn't be any tension in it. Okay? There's only tension in that rope because it's attached to another block that's resisting the first block. Think of it like this. None of you have probably ever towed a trailer. Okay? But like, imagine this. I'm driving my truck and I hit the gas, I accelerate really well. Now I hook up to a trailer, a big heavy trailer, and then I hit the gas. Well, I'm not going to accelerate nearly as well because there's this big mass behind me that's pulling backwards on me. I'm pulling forwards on it, it's pulling backwards on me, and it slows me down. I cannot accelerate at the same rate, even though I'm using exactly the same amount of force. Everybody follow? Okay. So the third force acting on the 10 kilogram block is the tension from the other block, the tension in the rope. So I've got 2 out of the 3 forces acting on the 10 kilogram block. I also know the acceleration of that block. Right now, can I find the net force on the first block? I can, because I can go mass times acceleration. I've got those 2 numbers, so I can do that. So 10 times 0.36 is going to be 3.6 newtons forward. Okay, that number is important because it is not only the net force, it is also the vector sum of this plus that. So since I have 2 out of the 3 of those, can I find the last one? Right? When I find net force, there's 2 ways to find it. I can go mass times acceleration, which is what I did because those are the numbers I had. But now I have to also understand that net force is also the vector sum of all the forces acting on the object. The 55 newtons, the 14.7 newtons, and this tension that I'm supposed to find. So the next thing I do then is I write that F net equals the tension in the rope plus force of friction plus the applied force. That's the 55 newtons forward. So I'm going to subtract these 2 forces over to this side. I do have to keep in mind which ones are forward and backward because that's going to matter. So I'm going to have F net minus the force of friction minus the applied force equals the tension in the rope. Am I doing anything different than any of the other problems we've done? Nope. M times A, sum of all forces. I've done nothing different than I have on any other question. So this is going to be F net, which we said was 3.6. Since it's forward, it's positive. Minus the force of friction, which is backwards, and it's 14.7, so that's going to be negative 14.7 newtons. And then minus the applied force, which is 55 newtons. Okay, so 3.6 minus negative 14.7 minus 55. Negative 36.7. That makes sense. The rope is pulling backwards on that mass. So it should be a negative number when I do it. Right? Well, I think we only have 2 significant digits though, so it's going to be 37 newtons. Okay? And it's going to be 37 newtons backward. Okay? Contextually difficult? Right? I mean, what math did we do there? Multiplied m times a, and then I subtracted and added the numbers. Right? Again, nothing that's going to tax your mathematical ability. What's tricky is getting to it. Now, I did say that you could solve it with the other mass, with the 20 kilogram mass. Okay? Some people find the 20 kilogram mass easier for this reason. Okay? The 20 kilogram mass only has 2 forces acting on it. The rope, the thing we're supposed to find, and friction. Now, they don't tell me what that force is. But in the first question, they told me the total force of friction was 44.1. And then in part B, they told me 14.7 of that is acting on the 10 kilogram block. So if I do that subtraction operation, I can figure out how much friction was left over to be on the last block. Everybody okay with that? That's the part that I find makes that one trickier to use. After you figure that out, it's probably easier to do the 20 one. Okay? So I do that and I get the force of friction here. All right, so the force of friction is 29.4 newtons. Okay, is the acceleration of this block still 0.36 meters per second squared? It is, because it's part of that system, and the whole system has to have that acceleration. Can I find the net force on the 20 kilogram block? I have mass, I have acceleration. Okay, I've got 7.2 newtons of net force forwards. I have 29.4 newtons worth of friction backwards. The only two forces acting on this block are friction and the rope. So, F net equals the force of friction plus the tension in the rope. I know that number, so I'm going to subtract it over. Okay, so I've isolated the tension in the rope. 7.2 minus negative 29.4. Pretty sure that comes out to 36.7 newtons or something close to it, and rounds up to 37 anyway. Okay, newtons, but now it's forward. Why? When I found the tension in the rope using the front block, it was backwards. Is that okay? Yeah. When you tie something to something else, it acts in two directions. Okay? That rope pulls backwards on the front block, but it pulls forwards on the back block. Right? As long as you put in the positives and negatives for forward and backward, you'll end up with the right direction. And it's okay if they're different in this situation. Okay? So again, this is why we spend so much time on Newton's second law. There's just so many applications of it, and you have to see a lot of them to start figuring out, oh, okay, this is the kind of thing that I want to look for. This is what I'm going to need in a question. Do I have mass? Do I have acceleration? Do I have enough of the forces to find net force by adding them together? Right? I know I always have to do those two things. Can I see the situation enough, visualize the situation enough to identify what I have? Right? And that's the importance of a free body diagram. Right? We always want to draw a free body diagram to help us find all those forces. Okay, I want you guys to try question number 1. Start with a diagram. Okay? It is very similar to this one, and it's an elevator at the same time. So, with this question, we've got this situation here. We've got 2 buckets of nails. The buckets of nails are the same mass. They're both 5 kilograms. Right? And it tells me that the tension in the rope connecting the 2 buckets is 60 newtons. Everybody all right with that? Okay. What other forces are in that system?
Gravity.
Gravity. Does gravity act on both buckets? It does. All right. And I can calculate the force of gravity on each bucket or on the system as a group. Here's my problem. I don't know that force. They don't tell me what it is. But if I understand that all parts of a system have the same acceleration, I only need to find the acceleration of one of the buckets. Agreed? Which bucket's my best choice, top or bottom? Bottom. Here's why. This 60 newtons worth of tension is pulling down on the top bucket, which doesn't help me, and up on the bottom bucket. So what I'm going to do is I'm going to say, bye-bye top bucket. I don't need you. And I'm going to deal with just the bottom bucket. Because I can calculate this force. because it's the force of gravity. And all I have to do to get it is m times g. 5 times 9.81 is 49.05 newtons. Is this now an elevator question? Okay, so I've got a force up and a force down. Can I do sum of all forces? All right, so 60 plus negative 49.05 should give me 10.95 newtons up. Right, so F net, right, was the force of tension plus the force of gravity, and then I just added them together and I got F net to be 10.95 newtons. Everyone okay with what I did there? I'm supposed to find acceleration. Can I find it now? I know mass and F net. So now I'll do F net equals m times a, divide both sides by mass, 10.95 divided by 5 kilograms should give me 2.2 meters per second squared up. That's the acceleration of the bottom bucket, the top bucket, both buckets. They're a system. Mathematically challenging? But man, do you have to be able to see into it. Okay? So challenging, that part of it. Being able to look at that and go, okay, I know I have to do these two things. I always have to do sum of all forces and m times a. Where can I get enough information to do those two things? Do I use the whole system? Do I use part of the system and then apply it to the rest? What do I have to do here? Right? That's the challenging part. Okay, we did one like this yesterday. Did we do this one? No, we did it. I just made one up, didn't I? Okay. We did one like that. Okay, try this one. That's a good one. All right, so I got a 20 kilogram truck tire lying on a miraculously frictionless horizontal surface. Those things don't exist, but man, do they come up all the time in our class. So we have a horizontal frictionless surface that the tire is on. There are two buckets hanging from either side over frictionless, massless pulleys. Magic again, right? So I've got those two pails and I've got the tire. I know the mass of all the parts. I want the acceleration of the system. And notice, they only ask for the magnitude of the system's acceleration. Why only the magnitude? Why can't you give a vector for the entire system? Okay?
Because one pail is going to go up and the other one's going to go down.
And the tire's going to go
In one way.
left or right, yeah. I can't give a vector in this situation. If they asked for just the tire, then I could. Okay? But in this case, they're asking, what's the acceleration, magnitude of the acceleration of the system? All right, I'll give you a few minutes here, see how you do on that one. Good. So with this one, since they want the magnitude of the acceleration of the system, okay, the first thing I want to do is draw on all the forces and then figure out, do I need to calculate that by finding one part of it, or do I want to calculate that by using the whole thing? Right? And you figure that out by looking at what are the forces you know. So they tell me that pail C is 6 kilograms and pail B is 8 kilograms. And the tire is 20 kilograms. So since the table's frictionless, the pulleys are frictionless, the only forces acting in this system are what?
Gravity.
Gravity and gravity on the two buckets. Right? That's what we have. So on this one here, we've got Fg, okay, which is m times g, so that's going to be 58.86, I believe, newtons. And then this one here will be 78.48. Since no one's arguing with me, I'm going to assume my mental math is okay there. All right, so now that we've got those two forces, am I doing this for just one part of the system or the whole system? Do I know the mass of the entire system? Do I know the only forces acting on the system? then I'm doing this as a system. Okay, if I only knew the forces acting on pail C, then I'd use pail C, and I'd just say, all right, I found the acceleration of pail C. Since they're all connected, that's also the acceleration of the system. But in this case, since I know all of the parts, I'm gonna solve it as a system, and it's gonna look like this. The system has a mass of 34 kilograms. It is being pulled this way by 58.86 newtons and this way by 78.48 newtons. That's what's going on here. If I'm talking about the entire system, I need the entire mass. Can I do sum of all forces at this point? There's only two forces. I know them both. So yes, I can definitely do sum of all forces. 78.48 plus negative 58.86 should be 19.62 newtons. And that would be this direction. I can't give a direction right now, so I'm just going to leave that as that force for right now. Now that I have the net force, and they want the acceleration, I can do that other thing I do in every single Newton's second law question, m times a. I'll find acceleration, 19.62 divided by 34 kilograms. All right, so the acceleration is 0.58 meters per second squared. And I leave it at that because I can't give a direction. And the question only asked for magnitude, that's it. Again, not much to that question in terms of what you write down on paper, but there's a lot that goes on inside your head, hopefully. Okay. I'm gonna, let's, no, I don't want to go into static. We'll go over static on Monday, but there are a couple of ones from your digital workbook that I want you to try before we run out of time. Okay, I would like you guys to do 20 and 21. Now, I will tell you, the trick with 21, okay, is something you have to watch out for because lots of Newton's second law problems will do this. You have to watch out for it because lots of Newton's second law problems will do this. Is a 725 Newton student. What did they give you there? They tell you somebody is this many newtons?
Force of gravity.
Right. That's their weight. That's their force of gravity. So that's m times g. So you could find their mass pretty easily. You divide that by 9.81, you'd have their mass. But lots of times a question will say, this box or this person is this many newtons. They're telling you the weight, not the mass. Right? It's just something to watch for because people sometimes misapply it. Okay. 20 and 21, of course. But